So last time we were doing these heating and cooling curves. Did I explain these heating and cooling curves, Azuni, last time? And I think we didn't do any question. So this is one of the most important topic. So let's try to do it again. I think this question we did. What is the freezing point? What is the boiling point? Yes, we did. Okay. 95 question. This question we did. Sketch a heating curve. This one we did. Okay, good. What about this one? We did this. I think this is the question which we have to do. Okay. This question we have to do, right? So we are starting with this question. This is based on heating and cooling curves. First, let's make a sketch. What quantity of energy means we have to calculate total amount of energy needed to convert 0.50. I'm reading the question, children. 0.500 kg of ice. Ice is solid to steam. So first the solid will get converted into liquid. Then liquid will get converted into steam. So we have to take care of these phase changes also. In the final temperature of the steam, they have given us 250 degrees Celsius. 250 degrees Celsius. So let's make the energy diagram, that the heating and cooling curves. If I make a curve, this is heat here. This is temperature. If I make a curve like this, children, what is that curve called as? This curve. What is it called as? Is it heating or cooling? High temperature to low temperature is like this. What is this curve called as? It's called as cooling curve. Yes, Aditi, very good. Cooling. You're going from high temperature to low temperature. And here the heat, this heat is released or needed. This is released. Because your cooling and heat is coming out of the system. Temperature of the system is going down. But right now, in this particular question, I have to make heating curve. So you draw the axis. Here is the temperature. So in the heating and cooling curves, the coordinates are temperature and heat. So what is the lowest temperature with which I have to start? Read the question. Pick up the temperature. Okay. Am I audible, children? Yes. Okay. 1 second, Lisa. Okay. Okay. Great. So Lisa was having some problem with the audio. So temperature. Temperature, I have to start from -20. See here. Do you know the melting point of ice? Melting point of ice. We all know freezing point, melting point. What is the melting point? 0 degrees Celsius. What's the boiling point of water? 100 degrees Celsius. These are important points. So I'm marking here. -20, I'm marking this one as 0 degrees Celsius. I'm marking this one as 100. My marking is not very accurate, but just to make you understand heating curve, and I'm marking this one as 250. That's the final temperature, children. This one, 250. Now let's start making the graph. So start from minus 20. Minus 20 to 0. What is the state of matter? Minus 20 to 0. State of matter. This is solid, liquid, steam. Steam means gas. So what is the state of matter from minus 20 to 0? State of matter means is it solid, liquid or gas? Minus 20 to 0. Yeah, state of matter. You know there are three states of matter around you. So if rather than saying solid, liquid, gas, if I say state of matter, then you should understand I'm asking whether the substance is solid, liquid or gas. So minus 20 to 0 is solid. So there is a rise in temperature. Graph will go like this. There is no change in the state. This is solid. What happens at 0 degrees Celsius? It start melting. Melting. This is melting, which we also called as fusion. And what is after that? After melting, there is further rise in temperature up to 100. This is liquid state. 100. At 100, boiling. During melting, boiling, there is no rise in temperature, right? And then, yeah, vaporization we can say. And after that, again, there is a rise in temperature up to 250. This is a gas. I'm marking them with the points A, B, C, D, E, F. Answer these questions. What is the state of matter at this point between A and B here? So I'm making a point here. This one. Okay. What is the state of matter at this point? This one. Solid and liquid. Aditi, both of them. BC is the line which represents the change of the solid into liquid. So both of them. What is the state of matter at B? At B. Yes, only solid. At C, liquid. But in between B and C, any point here, here, both the states are there, right? What is the state of matter at D? Only liquid. At this point, only liquid. At this point, liquid and gas. At this point, only gas. At this point, gas. At this point, gas. Next question. Why is there no change in temperature here? Where the heat is going? You can see this heat? This much amount of heat. Where is it going? Where is this amount of heat going? This box of heat. Where is it going? Explain where this heat is going. It's not showing you rise in temperature. There is no rise in temperature. Where it is going? That you should know. It can be a question. This is the phase change, right? So during phase change, you know the meaning of phase? Phase means solid, liquid, gas, the states of matter. During phase changes, heat is used. Heat is used in overcoming. In overcoming the IMFs. You're breaking IMFs. This is solid. This is liquid. Solid to liquid, you're breaking IMFs. So whatever amount of heat is there in this box, That's not showing you rise in temperature because it is being used in overcoming attractive forces. It's breaking attractive forces. It is used there. So no rise in temperature. In overcoming the IMF or breaking attractions. Breaking attractions. So no rise in temperature. Heat will not appear as rise in temperature. When heat is not doing any work, then it appears as a rise in temperature. So no rise in temperature. So children, please write on this in your notes. It's very important. Same here. Same here. I'm doing slight changes in this line. This is E and this is F. Okay. Now what is this heat called as? This one, which is helping you in melting. This is called as delta H of fusion, right? Delta H of fusion. So I'm writing here B to C is delta H of fusion. Fusion means melting. What is D to E called as? D to E, delta H of D to E. What's the process? Yes, this is called as delta H of vaporization. This question I have discussed 2-3 times with all of you. So once more, if you see my graph, delta, I corrected it also for this question only. Delta H of vaporization is more than delta H of fusion. Explain why. This is there every time. Explain. Explain why. Answer this question, children. So I'm trying to make my question more clear. This is my delta H of vaporization. This much heat. And this is the fusion. So you can see that vaporization is more than fusion. Why? And what is this heat? What are these heat doing? They are breaking the IMF. So in which case the IMF breaking is more during vaporization or fusion? Yes, but why? Aditi, Azuni, you are perfectly all right, but why? Because in gases, we have negligible IMFs. We have to overcome all IMFs. We have to break all the IMFs as we go from liquid to gas. But solid to liquid, what we are doing, Afan, your answers? Solid to liquid. What are we doing? We are simply making them weaker. Yes, Lisa, we are breaking IMFs, but we are making them weaker and they are still there. Liquids have IMFs, right? They are still there. But they are slightly weaker. So molecules are moving. They are not fixed like in a solid. So these are the important things which you have to retain. Anyone has any question here? Afan, are you there? He's in the class? Oh, yeah. He's sorry. Ice. Okay, good. So are we clear about the graph and the meanings? Now the question is calculate the total amount of heat. So I'm going to show you how to represent different amounts of heat. Check here. This is part 1. I need to know this heat. And this one is part 2. I need to know this heat. And this one is part 3. I need to know this heat. And this one is part 4. I need to know this heat, and this one is your part 5. I need to know this heat. So we have to understand what equation I'm going to use for different parts. So first one, I'm calling it as Q1, this one. Second, Q2. Third, Q3. Fourth, Q4. Fifth, Q5. And then I will say Q total. Q is heat. Q total, that's the question, total energy, quantity of energy. Q total is Q1 plus Q2 plus Q3 plus Q4 plus Q5. If I know Q1, Q2, Q3, Q4, Q5, I know Q total and my question will be answered. So please read the question again if you have any doubt in the question. This is one extensive question, complete question. But in the exam, the question, they break down the question into simpler part. Like they will ask up to here. Or they will ask up to here. Then you have to make heating curve up to this level only. They will say 100 degree, but it is liquid. Then you stop here. Calculate Q1, Q2, Q3. If let's say they are saying calculate the amount of heat when all the water is solid water is converted into liquid, then only this much. Stop at C. So you can stop anywhere in depending upon what they are asking in the question. You can stop anywhere. So number of questions are there. So this question includes everything. So let's see. Let's work with Q1. Yes, children, how to calculate Q1? Q1 is solid, ice, and Q1 equals to mc delta T because there is a rise in temperature. You can see the line, the blue line. Now read the question. What is M? What is M? Of the ice. M is the mass of the ice. What is it? 0.500 kilogram. You can see. But I cannot take in kilograms because if you see the specific heat capacity of ice here, children, is in grams per gram. So it means I have to convert 0.5 kilograms into grams. Then it means, yes, very good. So Aslesha is helping me. Please, all of you, do this mathematics, this thinking with me. 5.500. How many sig figs? 3. You can see that this number has 3. So put a decimal here. Don't put any more zeros. This is 3. C, what is C of ice? Is given in the question. It will be given to you. 2.03. This one. And what is delta T? I want answer for delta T. So come on the heating curve. See the delta T. You're going from -20 to 0. So what is delta T? This I'm calculating Q1 from A to B. Delta T is, yes, 20. What will be the final units, children, after doing all these things? It's Q1 is heat. Units will be joules. You can do the dimensional also. Yes, good, Azuni. So now solve it. Please use mathematics, calculator, and give me answer in 3 significant figures. 3 or 2? 2. This number has 2. You see? 2 significant figures. Give the answer in 2 sig fig. Otherwise, what you can do, you can put the answer correctly here in the final answer. we can go for 2 sig fig, right? In the final answer. So what's the answer here? Because they are not asking Q1, they are asking Q total. So I will worry about sig fig only in final answer. So don't worry about sig fig right now. We'll take care of the sig fig in the final answer. Okay, this is the answer given by Aditi, and Azuni is also giving same. So I take it as is correct. Now let's calculate B to C, Q2. Can I use this equation MC delta T here? B to C, this part. No, because delta T is 0. So what equation I'm going to use? If you remember in the cup calorimeter, there was an equation delta H reaction is minus Q of the water divided by N. But that is the case when we are carrying out a reaction. Here there is no reaction, it's just heating. So here I'm going to use this equation that Q2 is N times delta H of fusion. Delta H of fusion, is it given? Yeah. So do you know N, children? What is N? N is the number of moles. Number of moles. Mass of the ice is given 500 grams. So moles of ice. You know the formula of ice? Do you know the molar mass of ice, children? Molar mass of ice. Anyone? What's the molar mass of ice? Yeah, it's water. Ice is water. Very good, Lisa. 500 divided by 18.02. How much is this? These are the moles. How many moles? And plug in that here. 500 divided by 18.02. These are the moles of ice times this delta H of fusion, which is given in the question here. 6.02 kilojoules per mole. Mole cancelled. Can you see you are getting heat in kilojoules? How much is this? This answer. Don't worry about sig fig. Sig fig will take care only in the last for the final answer. So what's the answer here? Aditi is giving me 167.04 kilojoules. Is it okay? Check this answer, children. And this one is in joules, Aditi. And this one is kilojoules. Finally, we have to add them. So I think it's better to convert that into joules. Is this the answer? Who is checking? Yes, Azuni. Good. So this answer is also confirmed. Rest of all of you, are you doing your calculation? Afan is doing. Yes, good. Nivriti, you're understanding the concept? Nivriti, yeah. You're understanding everything, Nivriti? Ariba, good. So this is Q1, this is Q2. The way I calculated Q1, Q2, now you people are going to help me with Q3, Q4, Q5. Ready? Q3, Q4, Q5. Let's do it. Ready for Q3? So what is happening during Q3? The phase is not changing, but temperature is changing. And it is liquid. This one, this part. So which equation? Tell me the equation. Which equation should I use here? Yes, MC delta T. Perfect. What is M here? Same. Mass will not be created nor cannot be destroyed. Same. Whatever the mass was ice, exactly same mass. C, C, look at the question. Give me the value of C. C, you remember? Specific heat capacity of water, liquid water. And that is given to you in the question. You can see it? Yes, this one. Take this value, 4.2. Give me delta T. Look at the graph. Delta T. What is delta T? This temperature is 100. So what is delta T? 100. Answer will be in joules because C is in joules. What's the final answer? Is this the answer? Oh, 21. Okay. This is Q3. All these Qs have positive sign because it's endothermic. You can see you are heating, you are adding heat. So they all are with the positive sign. Now let's calculate Q4. This one. Children, you can see the Q4 here. This is Q4, this one. So there is no delta T. So what equation I'm going to use? N times delta H of vaporization. What is N? We calculate it here. This one. Because the mass is not changing. Yes, very good, Azuni. So N is 500 divided by 18.02. This is N, moles of the water, liquid water. Delta H vaporization. See, what is it given in the question? It's given in the question. Anyone? Give me the value of delta H of vaporization. Yes, please. Yes, 40.7 kilojoules per mole. But this is also mole. Mole and mole cancel. That's why this equation is valid. So how much you are getting? Calculate it. Calculate this heat. Q4. Yes, please. Q4. Okay, give me in joules. 1129 300 joules. Yes, Aditi, good. Azuni, good. Aditi and Azuni are helping me with mathematics. So they are making themselves prepared for the exam. Because in the exam, more faster you do this calculation part, more time you get for other questions. Exam is not free of time, means you can sit throughout the day. It has a limited time. You have to practice calculations so that whenever calculations are needed, you should be very fast with your calculator and can save time. Now let's work for Q5. You can see Q5, children. This is Q5, this one, this one. But which equation I'm going to use here for the Q5? MC delta T. Okay, now very fast, all of you. What is M? Here, this is steam part. What is M? Same, 500. What is C? C in the question. Read the value of C. You can see the specific heat capacity of solid, liquid, gas is different. So C is given. This is steam, gas, 2.0. What is delta T? Delta T. Yes, Aditi, perfect thinking. See, you have to be fast like this. Work with me, children. You're not listening, you're doing. So don't be in the listening mode. Be in the doing mode and keep helping me. And how much is this? 150000 joules. So you have Q1. You see, you calculated everything. This is Q1, value is here. This is Q2, value is here. This is Q3, value is here. This is Q4, value is here. As I said, this is a question in which we are going from this point to this point. But they can make a question, they can ask you to stop here. Then you have to calculate only this much. They may ask you to stop here, 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 like this. So you have to be very careful. If I have to stop here, what all I have to include, right? So what is Q total? Sum of all these. Now I'm using this equation, Q total. So Q total is, you're calculating it, children? Calculate Q total. All the big circles which I have made, highlighted one, just add them. And the answer should have two significant figures because one of the temperature is in 2 Siegfried. Okay. Azuni is giving me answer as 167. Is it correct? Let's convert this into kilojoules. Okay. So Aditi is giving me 1.7 times 10 raised to power 6 units, joules. So what will be the answer in kilojoules? You divide it by 1000. So 1.7 times 10 raised to power 6 divided by 1000 kilojoules. And that will be 1.7 times 10 raised to power 3 kilojoules. So can I write it for 1700 joules? Can I put it like this? This is two significant figures. So are we clear about it? This question is clear, children? These are called as heating curves. The same question can be in the form of cooling curve. They may say that there is steam at 250 degrees Celsius. There is steam at this temperature, at this, and you are cooling it. So first you will come here, then you will come here, and the graph will go in the opposite direction, like this, 250. So first 250 to 100, it is converted into liquid. Then it is converted into, this is liquid, here liquid. Then this is melting at this point. And then finally it is solidification. The graph will become like this. And the amount of heat will be exactly same. Oh, yes, sorry. Yeah, you're right. Kilojoules. Aditi, perfect. Yeah, kilojoules. Because we converted that into kilojoules. So 1700. So the same amount of heat when I'm doing the cooling curve, the red one, the same amount of heat will be released. Because heat can neither be created nor be destroyed. So whatever amount of heat is needed to go from -20 to 250, exactly same amount of heat will be released when I come down from 250 to -20. So any questions about heating and cooling curves? No? Let's do this question. Okay. For this, I need this diagram again. Are you sure that we have not done any error in the answers here? Because somehow this answer appears to be very big. Mathematically, are you sure we have not done any error? Afan, can you help me? Is this answer correct? This one? I think we have done error here with one extra zero. Is this correct? Because the answer appears to be very big. So I feel that mathematically our answer is too big. Method is correct. Ah, it's four zeros. Not, yeah, I place four. Yeah, one, two, three, four. That's correct. And this one? So what you can do that because we don't want to waste time of the class in just checking the mathematics. What you can do, you can work out this again. Okay, this question is there in that Zumdal book. You can take out the PDF and check. I'm sure the answer is not correct. This number appears to be very big. So I'm sure we have done, there is no error in doing the equation, mathematics. There is no error. Everything worked out nicely. All the equations are used at the correctly. Only in multiplication division we are doing some error. Okay, so you can check it. Is this one correct? Okay, fine. So please check it in your free time. I'll post the answer on the WhatsApp group also. Now let's see this. Consider a 75 grams of water at 125. So what is the phase of water at 125? That's the question. What phase or phases are present? Okay, first of all, what is the phase at this temperature? Yes, at this temperature, 125. The phase is gas. So it is gas. Now you are removing heat. Energy is removed. So cooling curve. So 125 temperature will drop to 100. This is 100. Then there is a phase change, gas to liquid. Then again temperature will drop to 0. This is 0. And then again there is a phase change. And then after getting converted into solid, there is again drop in temperature. So they are saying when 215 kilojoules of energy is removed, what is the state of matter? So you can calculate this Q, right? As mc delta T. You can calculate this Q as N delta H of vaporization. Values will be given to you for the specific heat. This is Q1, this is Q2. Keep adding them. Add Q2 and Q1. See if you are exceeding this or you are equal to this. Then from there you are going to decide. Then calculate Q3, which is MC delta T. So now you add Q3. Check. If this sum is greater than 250 kilojoules, if this sum, then it means the substance isn't here or here or here. The substance is liquid if the three are greater than 250. Not greater, lesser than 250. The sum is less than 250. If it is less than 250, then the state of the matter is liquid. It can be here anywhere. Then calculate Q4, which is again N delta H of fusion. Now add Q1, Q2, Q3, Q4, add them. Compare it with 250. If it is less than 250, then it means the substance is somewhere here. Then you add Q5, which is MC delta T, and add them plus Q5. If it is less than 250, then it means substance is somewhere here, less than or equal. So naturally, you will not get equal. You will get even great. You will get something like greater than or less than, right? So that's how you're going to predict what is the state of matter. So we are not going to do this question. This is just an application part, and AP is not into much. But you have understood the question. This is cooling curve. Okay, children, please ask your question if you have any question related to heating and cooling curves. Any questions? So what are the important questions which can come in the exam? One is this kind of graph and these type of questions, which are very easy. Sketching the graph, no, I don't think, but maybe yes, in free response, they can put it. They can put any question. So sketching of the graph can be in the exam. Then this is the question which can come in parts, not the whole question, because whole question is going to take so much time. So they may say, okay, how much heat is needed as you go from -20 to 50 degrees Celsius? How the graph will appear? This is -20. You will go to 0. This is 0. Melting, fusion. Then you go up to 50 only. So graph will end here, 50. This is Q1. This is Q1. This is Q2. This one. And this is Q3. Just add them to get Q total. Q1 MC delta T. Q2 N delta H of fusion. Q3 MC delta T. So they may ask question here like this. Or they can put the question like this also. See here. This is one example. Second example. You are starting with -20 degrees Celsius ice. And then the temperature is 100 degrees Celsius, but it is liquid. It's not gas yet. It's liquid. How much heat? That's the question. Then how the graph will go? Check, children. You start with -20, lowest temperature. You heat, reach up to 0. Melting starts. Now it is liquid. This is liquid. You heat, go up to 100. This is 100. Stop here. You have to stop here. Don't make another line because you are not changing the phase. Now you have to calculate Q1. This is Q1. Q1. This is Q2. And this is Q3. But if let's say in place of liquid, they say gas. then what happens? Any one of you? What happens? If it is gas, then what should I include here? Yeah, delta H of vaporization. Aditi, good. Now I have to stop here. And now I have to include this Q4 also. I will use Q4 if they are asking gas. I will stop here if they have written liquid. So you have to understand this concept also. So these are the examples of heating and cooling curves. The unit is done completely. Till now, I think all the videos are there. All the videos are there, children. So I'm going to post this video maybe by your morning today. Now we are starting unit 7. Ready? Very interesting unit. Sharing it with you. Anyone? Do you know the name of unit 7? Any one of you? What's the name of unit 7? Yes, chemical equilibrium. So first I'll make you understand the word equilibrium. What is equilibrium? You know that when you are like we are in army, so after every 2 years we are posted out. Not even 2 years, 1.5 year in India. My husband is in army, not I am. Okay, but I am with him. So after every 1.5 year, we are posted out to new place, far away in India, not a very good city, border areas, desert areas like this. So whenever we are shifting from one place to another place, in the army there is a culture that we keep helping each other because life is tough. So my neighbors, they help like in providing food and everything. Whenever we are reaching the new place, leaving one place, when we are leaving, I'm doing packing, my neighbor will be doing my cooking. Not one, alternately some. I'm getting food every day. So now this culture has reduced because of the facilities and everything. So when we reach new place, they try to make us comfortable over there and they keep asking, are you comfortable? Are you comfortable? Like this. What is the meaning of this comfortable? Comfortable means that you are back to your routine. Your house is working properly. Your office is, husband is going to office, coming back. Everything is settled down the way it was earlier. That is called as equilibrium. Equilibrium means that it is stable. So I can say equilibrium of any system is the most stable form. Most stable. When you go to a new school, initially you are slightly, you are not so comfortable because you don't know people. But what happens after 10, 15 days? You become very stable. You are in equilibrium with the rest of the students, teachers, the rest of the environment, surroundings. So equilibrium state is actually the most stable form of the system. You already know system, right? So every chemical reaction tries to get every every chemical reaction tries to get in equilibrium, right? Because that is the most stable form of the reaction and nature wants stability. So everything is in the equilibrium. Like if there is some disturbance in the earth crust, earthquakes, why they come? If there is some disturbance, then nature will try to adjust it to bring it back to stability. So earthquake is harmful, they can kill people, but after that the earth becomes stable. So nature is looking up in the direction of equilibrium And now we are going to understand this word equilibrium in chemical reactions, right? Okay, I'm giving you one example here. Very good example. Please understand equilibrium, then this unit is nothing. It's very simple. If you are not clear about the word equilibrium, then you will be learning, but not in depth. Like you will be struggling with the concepts. Ready? There is a reaction of these two. They are not reacting. Look at this graph. This is concentration. Whose concentration is zero initially when the time is zero? Whose concentration is zero? NO2. So NO2 is the reactant or product? In this reaction with these two things, what is NO2? The product. Yes. So it means the reaction is this. N2O4 giving you NO2. Now I'm writing this double arrow. This means reversible. This means reaction is taking place in both direction. And okay, balancing the equation also. This is a gas and this is a gas. This reversible arrow means the reaction is going in this direction and is also going in this direction. Okay. So that also represent equilibrium. Reaction is in equilibrium. We'll understand the word equilibrium more in detail. So right now the reaction is clear. Okay, I started reaction with N2O4. Look at this experiment. There is N2O4. Initially, when the time is zero, only N2O4. This is N2O4. So what is happening to the concentration of N2O4 as time is passing by, as the time is increasing, as the reaction is going on? This is NO2. These are NO2. You can see that NO2 are increasing. N2O4 are decreasing. Count the N2O4. 1, 2, 3, 4, 5, 6. 6 here. How many here? 1, 2, 3, 4. Only 4. How many here? 1, 2, 3. Only 3. How many here? 1, 2, 3. 3. How many here? 1, 2, 3. 3. What happened here? The reaction is not showing any decrease in N2O4. But initially there is a decrease. So this decrease is here. But after that, the N2O4 concentration is not changing, this part. Now let's see NO2. When the time is zero, what is the amount of NO2? Zero. After that, 1, 2, 3, 4. After that, 1, 2, 3, 4, 5. After that, 1, 2, 3, 4, 5. After that, 1, 2, 3, 4. Actually, it should be 6. I'm missing one. Yeah, this should be 6. This is also 6. After that, 6. Because 3 will give you 6. You started with 6, 3 has reacted. 3 will give you 6. It's 1:2 ratio. So here also I'm missing 1. Yeah, it's here. 1, 2, 3, 4, 5, 6. Can you see it's constant? Can you see it's increasing? I'm showing you the increase here, children, on the graph. This is increasing. So this is NO2, which is increasing. But at the same time, when N2O4 stops increasing or decreasing, at the same time, NO2 is also constant. See, at the same time. And there is no further increase and decrease in the concentration of NO2. This state is called as equilibrium. Is it okay? You're understanding the equilibrium? So the equilibrium is the state where there is no further increase or decrease in the concentration of the reactants or the product. This is equilibrium. I'm going to represent it with E, equilibrium state, E. But what is this? This part. Is this equilibrium? No. This one? No. This is called as change. Things are changing, right? System is trying to get the equilibrium because equilibrium is the most stable form, right? So system is trying to get the equilibrium. So it is change. System is changing, struggling, going in the forward direction, reverse direction to get the equilibrium. I'm going to represent it by C, the change. Any one of you, can you tell me what is this state when the time is 0? This is called as initial. Initial. When you just started the experiment, when t is 0, t is 0. This is initial. I'm going to write it as I. You are going to learn these tables. Initial, change, equilibrium. You're going to learn these tables. These are called as ice, and this is the reaction. So rice table. Children, are we clear about the equilibrium? The word equilibrium is clear. Of course, this rice table we'll learn in detail very soon. But right now, let's focus on the meaning of the equilibrium. Are we clear? Can you tell me why these reactions are struggling, fighting, undergoing a change? This is struggling situation, this one here, up here to here. Here to here, the system is undergoing a change. Why it is undergoing a change? On its own, you're not doing anything. You leave the reaction mixture, it will attain equilibrium on its own. The system will struggle, will fight to go in the forward direction, reverse direction to achieve the equilibrium. Why? Any one of you? Yes, Azuni, perfect. Perfect answer. Because equilibrium is the most stable form and nature wants stability. So nature is the one which is forcing this reaction to move in the forward, reverse, is asking this reaction to attain the equilibrium. Stability, yes. Are we clear about it? One more question before. Okay, Aditi. One more question before I start going more in depth. What happens at the time of equilibrium? When you see there is a system which is in equilibrium, what happens? The reaction stops or is still going on? What happens at the time of equilibrium? There is no further change in concentration of the reactant and the product, correct? There is no change. Does it mean reaction has stopped? The reaction has not stopped. So what is happening, Ariba? If it has not stopped. What is happening? The rate of the reaction is still going on. The rate Rate law you have done. The rate for forward direction is equal to the rate for reverse direction. Means reaction is still going on. Whatever is the rate, Azuni, it can be fast, slow, but the rate is going in both the direction equally. If one molecule of N2O4 is converted into, one molecule is converted into two molecules of NO2, at the same time, two molecules will react to give you one N2O4. These two rates are equal. So that's why it appears that nothing is happening. You feel that nothing is happening because concentrations are not changing. But reaction is still going on. Is still going on equally in both the directions. Please understand this word. This is a very popular question in AP. What happened to the reaction at equilibrium? So many children they say stopped. No. So for to retain this word that reaction has not stopped, there is a word we call it as dynamic equilibrium. Dynamic. Equilibriums are dynamic. Dynamic means changing, continuously going in the forward direction and the reverse direction. It has not stopped. It's dynamic. They keep adjusting themselves. Reaction going in the forward direction. Immediately, same amount of the product will get converted into reactant. Reactant to product, product to reactant. That is dynamic state. Dynamic means it's changing state, going in the forward direction and the reverse direction. It is not static. The equilibrium is not static. No, not static. Dynamic means the reaction is going in the forward direction as well as in the reverse direction. So, children, is this word clear? Equilibrium? Okay, now let's see this. Before we go on this word again, dynamic, let's try to understand the color. Can you see this experiment? The reaction was N2O4, which is a colorless gas. No color. This is N2O4. No color. Pure N2O4. Nothing else is there. Then it's undergoing a change to give you NO2, and then finally they are achieving an equilibrium. Equilibrium is achieved, right? This is brown in color. This one. You can see how the color is increasing. I'm writing here, children. This is only N2O4. Now some NO2 has come. NO2. You can see light brown color. Check color. What is happening here? Is there any change in the color? Okay, Azuni, can you give me the reason why there is no change in the color? Afan, there is no change in the color. Brown color intensity is same. Any one of you? And don't say reaction has stopped. Yes, say reaction is in equilibrium. In equal amounts in both the direction. Reaction is happening in equal amounts in both the direction. Afan, is it clear? Aslisha, you're there? What do you want me to repeat, Afan? Question was clear to you, Afan? Yes, okay. So Afan is asking us to repeat this thing. Any one of you ready to help? The question is After this time, there is no change in the color of the, there is no change in the intensity of the color. The color intensity is same. It's not increasing, decreasing. The question was why? Because there is no change. Color is due to NO2, right? NO2, the brown color you can see. The color is due to NO2. So during this time, there is no change in the brown color of the tube. Question is why? Afan, is the question clear now? So why there is no color change? Because there is equilibrium. Some children they write because the reaction has stopped. No, the reaction has achieved the equilibrium. Now the reaction is taking place equally in both the directions. Now there is no change in the concentration of NO2. So there is no change in the intensity of the color, right? Now Azuni is answering a question which is, I think, asked by Naisha. Naisha? Yeah. Naisha has asked a question, when would it change then? Any one of you? Azuni has already, and she has used a very good word which I was about to introduce, but she has already used it. Children, look at her answer. So where it will change? Here, the change, this is change. This one, it will change here. When the concentrations are changing, this is change, right? This is equilibrium. This is initial. And this state, check the word used by Azuni. That's the one which I'm using all the time. This is equilibrium. What is this particular part? Non-equilibrium system. The reaction is in non-equilibrium. And if you leave it untouched, don't do anything, just leave it. Come back after some time. It will be in equilibrium on its own. Azuni, perfect. Very good. So we are good? Okay, now we are moving on. So equilibriums are dynamic. Any question? What's the meaning of dynamic, children? Dynamic means Ariba, Aslesha, Nivriti. Your answers are not coming. Nivriti, your answers are not coming. Nivriti, are you there? Nivriti, you are not there? Yes, reaction is not static. Reaction is going equally in both the directions, in the forward direction and reverse direction. You know what is the outcome of this dynamic word? The word dynamic means that if you disturb the equilibrium, like I was telling you that your school is changed. You are in a school, happy, comfortable, going, coming, everything is going smoothly. But you all of a sudden you change the school. But what will happen? After some time, you will come to equilibrium again. That's the advantage of dynamic, right? Nivriti, please answer here. Yes, so Lisa, your answers are also not coming. Nivriti, she's not in the class. Lisa, okay. Yeah, keep answering, dear. Okay. If you are not in the class, the way Aditi told me that I'm out, stepping out, so you can inform me so that I don't call your names. Okay, now in the video, everybody will come to know. Nivriti, you are not in the class. Okay. So we are clear about the word dynamic. Now, I'm writing one equation and I'm going to tell you the equilibrium constant K. If you remember in unit 5, we did steady state approximation. We didn't do that. There is a topic steady state approximation. Just check and let me know whether we did it or not. Yeah, that's fine, Aditi. You started answering here. Steady state approximation. We did this topic, children. Check it. Anil, can you check and let me know? Because if it is not done, I'll cover it here. Azuni is saying we did. That topic is based on this concept of equilibrium. Okay, so let's try to understand a reaction. 2A is in equilibrium with B. Let's make the graph. A is the reactant. This is the concentration. This is time here, not temperature, okay? Time. I started initial, this is initial, with a zero concentration of B and with some concentration of A. So with time, concentration of A decreases. But at the same time, concentration of B will increase. This increase is more. Can you see the slope? Oh, increase, decrease is more, increase is less. Sorry. So let's draw it. You're aware of this, what I'm talking. Two molecules of A disappears. So decrease is more. The slope is a decrease. When two molecules disappears, one molecule appear. So increase is less, right? Then after some time, the concentrations have become constant. This is concentration of B. This is concentration of A. This one is initial. I'm writing here, initial. What is this called as, children? What is this? This part? Change, right? Change. Equilibrium are changing. Why are they changing? Because they want to come in equilibrium. So this is non-equilibrium state. Concentrations are changing. This is non-equilibrium state. System is fighting to achieve the equilibrium. And this part, equilibrium. At the time of equilibrium, there is no change in the concentration of the reactants and the product. Here, I will introduce a term, we call it as equilibrium constant. This is equilibrium constant. It's represented by equilibrium constant, capital K. And before this is called as Q. We'll understand these two terms, Q and K. K is constant, but Q is not constant. Q is changing. So I'm not going to call Q as constant. So what is Q? Q is something which wants to become K. So Q is changing continuously, and once it reaches the value of K, then Q is K, then system is in equilibrium. So Q and K, very important terms in this unit. First, let's try to understand K. I'm saying this system is in equilibrium. So what is the rate of forward direction? Rate for forward direction. Rate law. If it is elementary reaction. Unit 5. Some children are doing quizzes of Unit 5. They can answer. Rate for forward direction. Afan, you have stopped doing quizzes? You were doing it earlier? Afan, when are you going to restart? Yeah, but this time you have to do very seriously, okay? Spend some time with the quiz. You know, children, when you submit a quiz, I come to know around how much time you took to finish the quiz. 20 seconds, 40 seconds, 1 minute. That's not doing quiz, right? So all these things are visible to me. How much time you have taken to submit the quiz. But still, please come back and do the quizzes, all of you. Don't worry. I'm not interested how you're doing it. I'm interested that you are reading the question, trying to solve it. This is sufficient for me. Rate for forward direction, elementary step. So what is the reactant for forward? Forward means this one. What is the reactant? A. So I'm going to write this K. This is rate constant. This is different K. Concentration of A in elementary steps, the coefficient becomes the order. This we did in the last part. This is the rate of forward direction. Reactant is A, coefficient is 2. This is the rate law for the forward direction because here this I'm taking it as elementary, right? What is the rate for the reverse direction? Rate law for reverse. All of you give the answer. What is the rate law for the reverse direction? Mhm. For the reverse means, yes, Azuni, Aditi, and Lisa. Reverse means this. What is the reactant? B. Very good. But this time you're going to say K. This is not equilibrium constant. What is it? Rate constant. K reverse concentration of B. Yes. Very good. Perfect explanation. Now, at the time of equilibrium, what happens? These two rates are equal. So, rate for the forward direction, I'm writing this as RF in short form, this as RREV. Rate of the forward direction is rate of the reverse direction, right? Now plug in these expressions. What is forward? Rate constant, not equilibrium, rate constant for the forward direction, concentration of A raised to power 2, rate constant for the reverse direction, concentration of B. Are we good? Now isolate the constants. This is a constant, this is a constant. They are not equal because let's say the reaction is like this. This is A, this is B. Activation energy for A to B, very high. Activation energy for B to A, low. This is high value of K reverse. Activation energy, rate constant, temperature, Arrhenius equation, unit 5. So these are not equal. It depends which step is going A to B or B to A, which one is easier, activation energy. So review this part. So I'm going to isolate my rate constants. Isolate this. I'm going to write it as Kf, which is a constant value for the forward direction. K reverse, rate constant for the reverse direction, is concentration of B over concentration of A squared. This is a constant, very special constant called as equilibrium constant. So what is equilibrium constant? Equilibrium constant is the ratio of the concentration of the product raised to power is coefficient, not the order, coefficient in the balanced equation. Remember the balanced equation was this, 2A in equilibrium with B. So what is the product? B. Raised to power is coefficient, this coefficient. divided by concentration of the reactant raised to power its coefficient. And this is concentration. The word is concentration. Do you know the meaning of concentration? What's the meaning of concentration, children? Concentration means amount in the solution. How much amount in the solution? How many moles per liter? So concentration means amount in the given solution. But if I give you a solid, do you think you can write down the concentration of a solid? No, because solid is not in the solution. If I give you a liquid, pure liquid, like water, pure liquid, do you think I can write down the concentration of a pure liquid? No. Their concentrations will be taken as one. They are not the part of equilibrium, not the part. They are not the part of equilibrium constant. So before we leave this class, can we practice writing the equilibrium constant value for some reactions? Let me see. So because we are left with less time, so I would like to take you on writing the equilibrium constant for some reactions. Okay, let's do this one. Don't worry about the topic. We are writing K expression. I'll help you. Is the time still we have time? Yeah, 7 minutes. So we can do this question, children. So this is one important thing which you have to take from today's class. Very, very important. All these reactions are in equilibrium. They are asking you to write down the equilibrium constant. Expression for K. Before I do this, I want to give you one reaction from my side. As an example, N2 gas, we can express gases also as concentration. Moles per liter volume. Gases, they have this moles per liter as pressure. More moles per liter, more pressure. So pressure of a gas is concentration. N2 gas, 3H2 gas, giving you. Now children, please, we are doing. All of us are doing. You are not listening, you are doing. This is the equation. I'm writing the equilibrium constant. You pay attention, then using the same method, you will write for these reactions. We should learn this particular question today. It is the concentration of the product, which is NH3 here, raised to power this coefficient 2, divided by concentration of the reactants. Product of the concentration means concentration of N2 raised to power 1 times product of the concentration of the reactants, H2. This should be multiplied. Raised to power 3. That is key. No units, ratio of the concentrations, no units. It will have a fixed value because concentrations are not changing. These values are not changing in the equilibrium. So it will have a fixed value, right? Use this concept and remember solids and liquids, their concentrations are taken as unity. Can you write down the equilibrium constant expression for this equation? Can we do that, children? Aslesha is writing CO. She has taken here K, capital K, equilibrium constant, concentration of CO raised to power 2 divided by concentration of CO2. But she did one error, and all of you are doing the same error. Only Ariba is right. Afan, you are also done one error. I have written here. This is solid. Afan, Aslesha, do not include it. Yes, Nivriti. Nivriti, where were you? I was calling your name very loudly. Lisa, yes. Don't include solids and liquids, right? Okay. Now, can you write down the equilibrium expression for A? Now take care. No solids, no liquids. So what is K expression for this one? All of you please work. Azuni, you are there? Yeah. Let's do it. Yes, yes. Just the concentration of CO2. Nothing these solids. They have nothing doing with my equilibrium, okay? It's only the concentration of CO2 that's going to decide the value of K. Okay, ready for B? You're not going to include liquids. No liquids. This concentration is unity. Include this only. So this is slightly difficult to type, so I'm typing here, writing here. Hg2 2 plus divided by Hg 2 plus. This is K. Do not include this. Let's do one last question. This one. Ready? Without my help. Do not include liquids and solids. And who is this? Ariba. Very good. 1 over concentration of O2 times concentration of H2 raised to power 2. Is it okay with everyone? Can we do this last C part? That's very simple. This is not included. This is not included. This is not included. Only this. So K is concentration of H2 raised to power 2. So we started with equilibrium and we have understood the word dynamic equilibrium. We have understood that how the equilibrium is in the graph, how it is represented and how the concentrations they become constant. And then we have understood the value, the expression for K, how to write down the K expression for different equations. Very big thing we have done. After that, it's very simple. Concepts are there, but if you're clear about it, then you will see equilibrium is just a game. We'll do very fast. Okay. See you in the next class. If you have any questions, you can stay back.